Is this a deadlock? I start seeing BPMN models everywhere. By the way, did you know that sound BPMN process models never deadlock? Hi, my name is Andreas Hense and I make videos about business process automation. Today I'll talk about the soundness property of BPMN process models. The soundness property has been defined 30 years ago by Will van der Aalst, and I'll put a link to the paper in the description below. If a process model has the soundness property, it is guaranteed that every case will eventually terminate and there are no dead activities. Dead activities are definitely a modeling error. Why would you have an activity in your model that can never be executed in any case? The good news is that there is an algorithm that decides the soundness property for a BPMN model. Therefore, we can receive a warning by our modeling tool if our model is not sound. In this video, I'll go through the different aspects of soundness using the tool bpmnInvest by Thomas Prince. Let's go to the computer. So here we have the tool bpmnInvest open, and I'll first talk about the topic of synchronization, or sometimes also called proper completion. And we will first turn the analysis off because we didn't do anything yet. And I just start with a simple process model. There is a start event and then there is an AND split, so parallel gateway here. And then we have a task A. And another task B. And then we have an XOR join. And afterwards we have a task C. And then we're done. And yeah, you will probably have seen the problem here. If we start the token simulation, and we put a pause here, and let's say here, we can see that A is executed and then C is executed, and then there's one token in the end event, and then B is executed and C is executed again. So this is a problem if C, for example, is something like, pay invoice or something, then this would be done twice, and in general it's something that we don't want. So if we turn on the analysis here of the tool, we can see that there is no synchronization and there is no unique end event execution here. So the tool immediately tells us what's wrong, and it even highlights this XOR join here and says possible missing synchronization. And if we click on the question mark, there's some kind of explanation going on, what we can do to repair this, for example. So of course we can repair this by replacing, having a parallel joining gateway here, for example. So that's the first thing. The second thing, we'll just start with a new diagram, is dead tasks or deadlocks. And I'll do a process model here with something like the opposite of what we had before. So we have a task A, and we have a task B, and then we have a parallel gateway, we have a task C here, and an end event. And this is the typical case that you know already, the deadlock situation. If we do the token simulation, we can either go up here and then there is a token at this AND join, and this will be stuck. So there won't be any other token coming in here anymore in this case. And the other case is similar. So let's look what the tool analysis is telling us here. So it says guaranteed termination is violated, unique end event execution is violated, and no dead activities is violated, and we have possible deadlock. It's showing us what's wrong here, and of course some hints on how to repair this. So this is of course a deadlock if the diagram is like that, but what we can do is we can put this into some other context and then make it work nevertheless. And so let's try this now with an AND split here. Parallel gateway, and we have task D, and then task E, then we have an XOR join, and then task F. Now, if we look at this model now and we put on the analysis here, I mean, the analysis is even worse. So we also don't have synchronization anymore, and we have these problems with the deadlock. And in fact, the context doesn't solve the deadlock problem in general, as we can see if we put on the token simulation. So token simulation here, let's say we put a pause here, and we take the upper branch. What's happening now? We get two tokens here. We have two tokens in front of F, and we can fire one of them, and then this goes here, and then we can fire the second one, and this goes up here, and now we have two tokens deadlocked here because they all came from the upper incoming flow, and there is no token on the lower incoming flow, so it's still deadlocked. But what if we implement some kind of clever logic in this splitting exclusive gateway that does something like distributing a token once to the upper branch and once to the lower branch. So if we do that again, and we imagine that there is some kind of clever logic implemented here, we can first have one token to the upper branch, and then there is this toggle going on, and then we have a token going to the lower branch, and then this is executed. So this example shows that depending on the context and depending on the concrete model and the concrete automation of your process model, this model can make sense, although it has all these flaws. But of course, I mean, in general, you wouldn't want to do that. If you would do that, you really have to know what you're doing here. Okay, so next one is boundary events. Boundary events are also nice. So we have a task A here, and let's now say we have a boundary event, and the boundary event task is going into some kind of XOR join, and this one is going in here as well. So let me just fix this arc here. And then we have a task B, and then the process ends here. So what's going on now? Now we have the boundary event, and this is an interrupting boundary event. So interrupting boundary events in combination with the XOR join are perfect because we have all the nice properties. But what I wanted to do is I wanted to use a non-interrupting boundary event. So I have to change the type here, and I take the message non-interrupting boundary event. And now, because this is non-interrupting, we have a problem. So synchronization isn't given anymore, and unique end event execution isn't given anymore. That's what the analysis tells us. And if we do the token simulation, I can show you what I mean. I just make a pause here, and I will now put a pause here as well. So one token comes from here. Then we finish this. Now you can see we have two tokens here. We can execute B twice. And in general, this is not what we want. So it doesn't have the soundness property. We can try to repair this by replacing this XOR join by an OR join. Let's do that. And now what does the analysis say? Now it says it's okay, although it's still problematic because, let me show you the token simulation. We can have more than one boundary event happening. So if we have one here, another one here, so these two are waiting now because of this token here that's still here. So the OR join is waiting, and now we release that. Now all tokens go here, and now you can see we have actually two tokens here, and this is the correct token game, and we can execute B twice. So we still have no soundness property here. Let's look at this definition of soundness in a little more detail. Here on the left-hand side, I have the citation from the paper I was talking about. It says, for any case, the procedure will terminate eventually, and the moment the procedure terminates, there is a token in place O, and all other places are empty. What is place O? So in this original definition, we always assume that we have a unique place E, and the place is an event here in this context, and we also have a unique place O, which is the end event, and that if there is a token in place O, all other places are empty. And this is what is sometimes called SESE, single entry, single exit. And this is a principle that's also very nice for the theory, and therefore the soundness definition is based on this SESE principle. BPMN has the meme principle, multiple entry, multiple exit. So how can we map BPMN multiple entry, multiple exit process models to this single entry, single exit? And the answer is this. Let me just delete those for a moment again. So if we have a BPMN model, and BPMN models, for example, can have more than one start event. So I have two start events, let's say. Then I have a task A. Here I have a task B. And then we have end events here. And in BPMN, we can also have what is called implicit start events. So we can just have a task here called C, and then this can have its own end event. If we now look at the analysis, it will say, it has the soundness property, but best practices haven't been used. And what is meant by that is here implicit start event. So this is highlighted blue, and it says, don't use these implicit start events. And anyway, but what happens in the token game here? If we start the simulation, and we start, let's say, with this start event, you can see now that we have a token here and a token here. So every time there is a start event, we automatically get a token from an implicit start event, and then we can just finish these things here. And likewise, if we have another case here, we have these things going on in the same manner. And now if we want to map this to this single entry, single exit, what we have to do is we need to first create our unique input condition, create our unique output condition. Now we transform all end events to intermediate events. And all start events to intermediate events. And now we start the whole process with an inclusive gateway. And the inclusive gateway now must make sure from its logic that it always sends a token to the implicit start events, like here for C, and that it sends exactly one token to one of the explicit start events. And at the end, we just join everything with the inclusive gateway. Now, if we turn on the analysis, we can see that everything's fine now. And yeah, and this is how this meme process model is translated into a SESE process model, and we can apply the soundness property here for BPMN models. Thank you for watching.